Good afternoon. I'm very happy to be here talking with you today. I hope I get to speak with a lot of you individually. As Trevor said, my name is Emile Hoskinson, Director of Product Management at D-Wave, responsible for our product and technology roadmap. D-Wave has been around for a while. I joined about 14 years ago. And when I was talking with the folks at D-Wave before I joined, there was a couple of things that really impressed me about them. One was that it was this small startup with big ambitions to build a quantum computing system with commercial value differently than a lot of the other players were considering. And as I talked with them more and learned about what they were focusing on, I was particularly impressed by what they were focusing on at the time, which was control circuitry. Boring classical control circuitry on chip for distributing and applying the biases and control signals necessary to scale up. These are the kind of thing that is not necessary for a lot of the scientific experiments that folks were focusing on. Not necessary for sort of increasing the impressive scientific experiments, but absolutely necessary for scaling the technology to become commercially relevant. And this was, 14 years ago that they were really getting going on this. It's been quite a long journey since I joined. I've been lucky to be a part of the team that has brought to you the Advantage system into the commercial realm, bringing value to customers today. Okay. You've seen this picture a few times today already, and I really like it. It conveys the complexity of what we're doing. It's also a picture taken by our marketing team because it looks impressive, and it does. I love it. But it's also real, and I'll take a few minutes to tell you a bit about it. The first thing you see in this picture is the wiring. It's like a mass of copper spaghetti. There are more than 200 individual control lines that come down from room temperature through our cryogenic refrigeration system and ultimately connect to the processor that sits behind that gold shield in the middle. And it seems like a lot of lines, but in fact, those lines are used to program and control more than 100,000 on-chip control circuits that are in the processor and are necessary to set up the problem to be solved and guide the evolution of the quantum wave function to a solution to the hard optimization problem that you need solved. So this is a feat of engineering that, like I said, beginning is absolutely necessary for scaling to commercial. And it sort of underlies, it's a key feature of the Advantage system and of our plans to continue scaling our technology. There's something else about this picture that's less obvious that I'll tell you. If you look at the sort of white string that, here, I might even be able to point to it. Let me try this. Okay, if you look at one of these bundles of copper wire are tied up. And now this everything you see here in one of our systems is embedded in and is surrounded by multiple shields, and the whole thing is cooled down to just a hair above absolute zero cryogenic temperatures in order to protect the quantum processor at the core from the heat and the electromagnetic radiation that's all around us. So these copper bundles are tied up here with something we affectionately refer to as a specialized cryogenic filament. It's actually dental floss. Okay, moving on. So that's a real picture. It's impressive and it's real. There is two types of quantum computing. Actually, there's more than two types of quantum computing, but I'll focus on the two dominant paradigms. One is annealing quantum computing, which forms the basis of our Advantage system. The other is gate model, which we are also pursuing. It's further away. Annealing quantum computing is specifically designed for optimization problems. And so an example of an optimization is delivery schedule. You've heard multiple examples throughout the day. Now, the optimization problem is specified by a cost function, and that can literally be the cost of implementing, say, the delivery schedule that is a solution to the problem. That cost function is parameterized by a set of decision variables. Okay, that decision might be whether employee A is going to drive the truck or employee B is going to drive the truck, or which truck, this truck is going to come before this one. There's a set of decision variables that ultimately specifies the schedule. And then there's interactions between those decisions. If an employee drives the truck, then that maybe influences whether another employee, when another employee drives, or something like that. So this is we have a graphical representation of this cost function where the decision variables are these arrows. Those in the processor are represented by qubits, and there are interactions between the qubits that encode the interactions between these decisions in the optimization problem. So those are physically programmed into the processor. The quantum annealing algorithm leverages quantum effects to find low cost or low energy, we refer to, solutions to this problem. And this is this configuration of qubits or decision variables that specify the solution to the optimization problem. Okay, so that's annealing quantum computing and underlies the core of our Advantage systems. There is gate model as well. And again, DWIV has a robust program to develop this. However, it's further away. Gate model is much closer to classical computing in the sense that what you do is you apply a sequence of gates or logical operations. This can be, say, taking an individual qubit decision variable and flipping it. That's one gate. Or it can be taking two qubits and entangling them, forming a quantum state, quantum interaction between them. And you perform a prescribed sequence of these gates to implement your algorithm, and then the configuration of qubits at the end encodes your solution, and you read that out, and that's the result of your computation. Okay, so gate model remains years away from commercial applications. And so why is that? One of the reasons for that is simply that, okay, there's a famous quantum computing algorithm, Shor's algorithm, which is one of the first algorithms that provably gets you a speed up over known classical alternatives for factoring integers. And if you can run Shor's algorithm on a quantum computer, you can break popular encryption schemes. So that is one motivation for building an error-corrected quantum computer, error-corrected gate model quantum computer, because that is what is required to run Shor's algorithm. An annealing quantum computer does not run Shor's algorithm. There's also other applications, quantum chemistry, and so on. Perhaps a better reason to develop a gate model system is that they're incredibly flexible. Perform the right sequence of gates, and you can really generate any quantum state you want. You can manipulate the quantum wave function represented by this collection of qubits in any way you want. It's very flexible. That flexibility, however, comes with a cost. the sequence of gates that you implement for a particular gate model algorithm is susceptible to corruption from decoherence. You really need error correction. That is not available on gate model systems today. You need millions of qubits to run something like Shor's algorithms. The current systems are really only at hundreds. So instead, companies that are developing gate model systems are focusing on what they call the NISQ era, the noisy intermediate scale quantum, and asking, okay, are there algorithms that we can run in the NISQ era? Well, one of those application areas is optimization. And there have been multiple algorithms proposed for NISQ era gate model systems to run optimization algorithms, including quantum approximate optimization algorithms, including variational quantum eigensolvers. So we can ask, how do those compare against quantum annealing? In every case that I know of, you can take an optimization problem and you run it on an existing gate model system, run it on an annealing system. And the annealing system wins by a wide margin. This includes the Quantum Economic Development Consortium, which has proposed using optimization use cases to benchmark quantum system and compare their performance. Another somewhat more technical reason for why the gate model systems don't perform as well is because these algorithms, variational versions of these algorithms, have parameters that need to be tuned, and that tuning actually makes use of classical computing resources. And the tuning can itself be quite hard, just as hard or harder than the optimization problem you want to solve. So there are significant barriers to optimization with the existing gate model systems. Okay, so what about the future error corrected? Error correction is a ways away. Once it does arise, can it compete with annealing and optimization? There's a lot of evidence that suggests that that will not be the case. And that has to do with the classical processing required to do the error correction. The encoding and decoding that's necessary using classical compute resources essentially removes the advantage that you get from running these optimization algorithms. So the message is that quantum annealing likely has a long-term advantage in optimization over other forms of quantum computing. It's specifically designed for optimization. We think it will be the choice for optimization even when gate model systems are eventually developed. Okay, so quantum annealing, again, forms the core of our Advantage system and is commercial today. There are multiple areas, application areas, use cases where our customers are using it. And that's because existing systems, the Advantage system, has more than 5,000 qubits. It is more resilient to errors. I'll talk a little bit more about that. It doesn't require significant processing or tuning. It really is a near-term, large-scale quantum computing technology. So now, one of the things I really want you to take away from my presentation today is an understanding of the basics for what quantum annealing is, how it works. So I'm gonna try to explain that. And I thought of an analogy when I was reviewing my slides last night, preparing, that I'm gonna try. I'll get to that. But as I showed before, one way of visualizing an optimization problem is through its cost function, is via these decision variables, which are represented by qubits and the interactions between them. Qubits are the decision variables. The cost function is represented by biases on those qubits, biases on those decisions, and the interactions, the impact one decision has on another. That's all programmed physically into the processor. The annealing algorithm makes use of quantum effects to find those low energy, low cost solutions. Okay, in this system, cost translates to energy, and annealing helps you find those low energy solutions. Annealing is inherently more robust. Okay, so now imagine the system interacts with the environment. Some heat from the environment causes a qubit to flip. Okay, in a gate model computation, that might corrupt the whole computation. In this case, it just changes the decision variable. And the annealing algorithm continuously tries to evolve the system to find lower energy states. So first of all, that after that error, it's still a solution. It may not be optimal, it's still a solution. But then the annealing algorithm can recover and find a lower energy state after that error. So it's more robust. This is somewhat technical, but once you've programmed in the biases and the interactions using those 100,000 circuits that I talked about at the beginning, the annealing algorithm can be implemented using a single global control signal, whereas with gate model, you really need individual fast control over every qubit. It's much harder to scale. Okay. So this is a summary, and I'll go over this. We'll go over the steps in more detail. Summary of how annealing works. You start off with no biases or interactions. You start off in a quantum state in which all solutions are equally represented. It's a giant superposition where you're considering all states with no biases. And then you slowly start to turn on the interactions and the biases associated with your cost function. At the end of the computation, you aim to find the optimal lowest energy solutions. I'll go through this step by step. At the beginning, again, no interactions or biases equals superposition of all possible solutions in your quantum wave function. Now, the analogy I thought of last night is, imagine this orange line, which is supposed to represent the solution cost as a function of solution configuration, decision variables. Imagine that's the bottom of an ocean or a lake, and there's water above it. And the level of water represents the probability that you will find a given solution at the end of your quantum annealing calculation. And so here, there's no interactions, there's no biases, so every configuration is equally probable. Your depth of your water is flat. Okay, now you start to turn on the interactions. The cost now varies with solution configuration. Now imagine what the water is doing, okay? It's deepest where the cost is lowest. And the depth of the water represents the probability that you will end up in a solution corresponding to that cost. So that's great. Okay, so let's keep that going. What you start to see is the appearance of local minima. And as you continue that, and remember, we're turning on the interactions, strengthening the biases, this cost function, water can get trapped in a local minima. And that's where the quantum mechanics come in, because you can have tunneling from one minima to the other. Basically, the water can flow through these barriers, quantum tunneling, right? So the reason I like this water analogy is because the water, you can easily imagine the water spreading out, and that's what the quantum wave function does. Quantum wave function represents the probability of finding a given solution. Water will spread out, and probability will be distributed until you have turned on the interactions long enough that you expect all of that probability, all of the water to localize in an optimal solution. And quantum mechanics helps you get there by tunneling through the barriers. So that's the analogy. I like it. I think that works. Okay, in the end, your solutions are classical and stable, and that's what you read out, and that's the solution to your optimization problems. You've got your decisions. Okay, so that underlies the core of our Advantage quantum annealing quantum computing system. It's got more than 5,000 qubits in it. There are multiple systems available globally with high uptime for production applications. And with our sophisticated hybrid solvers, we can leverage the best of the annealing quantum processing unit and classical compute resources, put those together to solve large-scale applications. Okay, but we're not going to stop there. we're going to continue innovating. Okay, I'm an experimental physicist by training. I love innovating. I love running experiments, coming up with new ideas. The team that I work with is excellent at coming up with new ideas constantly. We're always going to be evolving the technology. As I said at the beginning, I want to keep it focused on bringing quantum computing to the commercial realm, expanding application space and use cases so that innovation has a focus. You bring those two together, bring that focus and that innovation. And what we have next is the AdvantageTM system. We'll be releasing that this year, soon. And it will be able to solve more complex problems with higher connectivity and a new Zephyr topology. It'll give you higher quality solutions because of an increased energy scale. Okay, the energy scale is somewhat technical, but I can use that water analogy again. The energy scale has to do with the depth of the landscape and the depth of the minima with respect to each other. The deeper those are, the more water will tend to collect in the low-cost, low-energy solutions, and you'll be more likely to get those high-quality solutions. So that's important. Higher precision is also important. That allows you to distinguish between minima that are close together. Sometimes you want a variety of minima. Sometimes you want the absolute lowest, even if it's nearby another one. And the noise means that the noise means there's waves on the water, and the water's sloshing around. Okay, so then it's the water can splash over into other minima. If you have less noise, there's lower fluctuations. The water is calmer, and you can more easily distinguish those minima. So that can be quite important. The system will have higher coherence, and that is related to how easily this quantum wave function represented by the water spreads around and is able to find the lowest energy solutions, able to tunnel through barriers. Coherence, higher coherence allows it to flow more easily and find the optimal solutions faster. So our AdvantageTM system, we'll be releasing it soon. We have had a prototype available since last year. If you want to hear more about the details, the technical details of this system, at the scientific track tomorrow, we'll be talking about quantum simulation. We'll be giving a preview of the performance of the AdvantageTM system. Our customers haven't waited, so we put this prototype system online last year. And in the past year, we've had about 62 different organizations test out problems on it, submitting over 10 million problems. So there's a lot of pent-up demand, a lot of interest in this, and we think this is going to take quantum annealing and quantum optimization to the next level. So that's it. Thank you.